You're ready to go.
Okay, welcome everyone to the second public key encryption session of Hierarchical 2020. So we will start with co-chairing this session with Nontight Lee. And the first talk will be by Dimitris Kolonelos on incrementally aggregatable vector commitments and application to verifiable decentralized storage. So,
okay, can you hear me?
Yep. Yeah.
Great. So, okay, thanks for the introduction and thanks everyone for joining. So my talk is going to be, as the title indicates, about vector commitments. I will directly start with explaining briefly what these objects are. So vector commitments are primitives that allow you to take a vector, commit to it, so that at any later point you can selectively open any of the positions of the vector, meaning that you can output the value of the committed vector together with an opening proof that testifies for the validity of this vector, of this value. So for security, we demand position binding that intuitively says that you can uniquely open each position of the vector. And the interesting property of the primitive is that is succinctness, which says that the commitment and each opening proof should have size at most polylogarithmic in the size of the vector, or of the vector. So then a further property that was introduced last year by two independent works is subvector openings, which states that you can open many positions of the vector at once with a single opening proof. Meaning that this opening proof about the many positions now should be succinct, should have the same size as it would be for a single position. And here is a table that summarizes the previous works in the area. There are different constructions from different assumptions and with various properties. Now, it is worth noting that before our work, the only known construction that could support subvector openings and has constant size parameters is the work by Bonnet et al. That is working over groups of unknown order. And finally, there are also some concurrent works, one of which also appears at Hierarchical tomorrow at a different session. So going to our contributions, we continue the study of vector commitments by first of all introducing a new notion called incremental aggregation. And we saw two applications of incremental aggregation. One has to do with speed up the opening of vector commitments by preprocessing. And the second application has to do with the decentralized storage problem, for which we formalize a primitive called verifiable decentralized storage. So in construction side, we construct two incrementally aggregatable vector commitments, and then based on them, we construct two verifiable decentralized storage constructions. So incremental aggregation, I will explain briefly what this property is. First of all, aggregation in vector commitment or in vector commitments means to take two opening proofs and merge them into one for both positions. So incremental aggregation means to have the ability for unbounded aggregation and unbounded disaggregation. So unbounded aggregation means to have the ability to arbitrarily aggregate opening proofs for different positions and as many times as you want, unbounded times. And unbounded disaggregation is the inverse operation, which states it is the ability to take any arbitrary aggregated proof and disaggregate it for any subset of its positions. So these two properties, unbounded aggregation and disaggregation, give incremental aggregation. Now the first application that we said is committing and opening with preprocessing, and this is motivated by the fact that in vector commitments, the opening time is inherently at least linear in the size of the vector. And since the vectors can be large, we propose a preprocessing method in order to overcome this limitation. It consists of an offline phase and an online phase. In the offline phase, you compute aggregated proofs that cover all the vector or the positions of the vector. And then at the online phase, you receive a query. Normally, you have to disaggregate some of the aggregated proofs of the offline phase in order to get one opening proof for each position of the query, then aggregate, and then finally aggregate back in order to answer the query. And since these disaggregate and aggregate methods are faster than computing from scratch the opening proof for the query, this operation is faster than linear. So we also propose a trade-off between the storage overhead of the offline phase and the online time. And finally, we propose an algorithm in order to compute all of these proofs of the offline phase in less than quadratic time, in quasi-linear time. And the quadratic time would be the naive way to compute all of these proofs. Going to our constructions, we said we have two constructions. The first one builds on the BBF vector commitment. The second one builds on the CF13 and LM19 vector commitments. So our constructions are in the last rows of this table, and both are over groups of unknown order, have constant size parameters, can support subvector openings, and finally, of course, they can support incremental aggregation. And to our knowledge, these two are the only constructions that we know that can support incremental aggregation. So that's it. The final application that we said has to do with a decentralized storage problem, and that is to take some file and store it and have it stored by a distributed network in a verifiable way, for which we formalize a primitive. I don't have time, I think, to go through into many details of the problem. So yes, for more details, you can advise either the longer talk or the paper, the full version of the paper. So thanks for your attention.
Thank you very much, Dimitris. I don't see any question. So I would like to ask one. So this B trade-off that you mentioned, so what would be, how would you choose B in practice?
Yes, you would choose B according to how much memory you can afford or how much online time you would like to spend in the online phase upon a query. So if you have a limited memory you can afford to spend for the vector commitment, yes, I mean this parameters characterizes the the trade-off.
Okay. So, but do you think it would be what do you okay. Yeah, well, anyway, I have some question, but here there is another one in the chat from Koan Nguyen who asks, why doesn't the Merkle tree-based approach allow subvector opening?
Subvector opening, yes. So in Merkle trees, it's kind of inherent that you have to give the Merkle path for each opening, for each value that you need to open. So if you want to open many values that are in arbitrary positions, you have to give both Merkle tree paths. You cannot merge Merkle tree paths unless the positions are structured, they have some kind of structure. Otherwise, if they are I don't know, in arbitrary positions, you shouldn't be able to merge Merkle tree paths.
Okay, thanks, Dimitris.
Thank you.
Yeah, and the next talk is about the paper entitled Collusion-Resistant Trace and Revoke for Arbitrary Identities from Standard Assumptions. And the authors are Sam Kim and David Wu. But unfortunately, the authors cannot join this session, and instead they provided a 5-minute video. So maybe Kay will play this video, right? Kay?
Actually, I believe Kevin was supposed to. Would he
sorry.
like
Kevin?
to?
Give me a moment here.
Yeah. Thank you.
Any appearance of organization on our part is purely an illusion.
It's true.
Hi everyone. Unfortunately, I will be traveling on the week of.
Don't forget to share the screen.
Thanks for the help.
I aim to help with technical bugs. I can also play it if you can't get it running.
Run some music. Just a moment here. I've got it.
Sure.
Hi everyone. Hi everyone. Unfortunately, I will be traveling on the week of the conference, so I decided to record my 5-minute talk. So the title of this work is Collision Resistant, Trace and Revoke for Arbitrary Identities from Standard Assumptions. So there's a joint work with David Wu. So I'll be talking about trace and revoke schemes in this talk. So let me start by defining and motivating this concept. Let me do this in a sequence of steps. So let's begin with a simple shared key.
Sound cut out, Kevin.
Messages to everyone in the group. Well, we can do this very simply by generating a public key for the group and then providing.
I'll back up just a little bit.
And we want a way to be able to encrypt messages to everyone in the group. Well, we can do this very simply by generating a public key for the group and then providing everyone with the corresponding decryption key. So whenever someone wants to broadcast out a message to the group, it can encrypt the message under the single public key and broadcast it out to the network. Then since everyone in the group holds the shared decryption key, everyone can decrypt the ciphertext. So this is all nice and fine, and the system is secure under the assumption that the shared key is managed properly by everyone in the system. But now let's consider the scenario where this assumption does not hold and the key is not actually managed correctly. So suppose that there is a malicious member in the group that leaks the shared key to the open internet. If this happens, then since the shared key is out in the public, we cannot have any security in the system. If this happens, then from the perspective of the company, it will want to be able to identify who the employee was that leaked the shared key. It will want to be able to trace the traitor so that it can punish the traitor and prevent this from happening again. So, but in this simple shared key system, since everyone holds the single shared key, there is no way to tell who was the one that actually leaked the key. So this is where traitor tracing comes in. So this is an old concept that was introduced by Choi et al. In 1994. In a traitor tracing scheme, everyone in the group holds a key of its own. So the scheme still guarantees broadcast functionality as before, in that if we encrypt under a single public key, then everyone in the system can decrypt the ciphertext. Okay? But when a malicious member leaks a key to the outside, then there is a tracing mechanism that, when given access to what was leaked, can correctly point to the traitor that leaked this key. So this is basically the idea of traitor tracing. What makes constructing a traitor tracing scheme highly non-trivial is the way we model this leakage of key. So we usually model the malicious member leaking the key as creating a decoder box. And intuitively, we can think of like a decoder box as some like decryption software that has the malicious member's decryption key embedded inside it. And the software can be in any form and it can be highly obfuscated. So we need to design a tracing algorithm that can interact with this decoder box in a black box way and identify the traitor. So, right, that's the concept of traitor tracing. Finally, trace and revoke, which this is a concept that was introduced by Nauer and Pincus as a further extension of traitor tracing. So let's say the company was able to identify that Bob that Bob was the one who betrayed the group and created the decoder box, can the company revoke Bob's access to future ciphertext without going through some sort of a complicated key rotation procedure? While trace and revoke allows us to do this, so in a trace and revoke scheme, the encryption algorithm additionally takes in a blacklist of users or what is called a revocation list or revocation set. So let's say the resulting ciphertext is broadcasted out to everyone in the system. Then everyone who is not in the revocation list can decrypt the ciphertext. Everyone in the revocation list cannot decrypt the ciphertext. So this is the concept of trace and revoke scheme that we deal with in this work. There are a number of ideal properties that we may want from a trace and revoke scheme. So our goal in this work was to achieve a trace and revoke scheme that achieved all of these ideal properties while only relying on standard assumptions. So in this work, we give a new construction that is fully collision resistant. It is identity-based. It can revoke an unbounded number of users. And we only rely on the hardness, on the standard hardness of L degree for our security. So there are a number of existing trace and revoke schemes in the literature that uses many elegant ideas, but none of these constructions achieves all of the properties that are listed here. And so for trace and revoke schemes, generally, ciphertext size is a metric that we use to generally judge the efficiency of a construction. So for our scheme, the size of the ciphertext does depend linearly on the size of the revoke set, but the size grows logarithmically with the number of bits needed to represent each of them. So I discuss more about this in the full version of this video. So please refer to the video for more information. And that's it. Thank you very much. Hi, everyone.
We don't have the speaker here to answer questions. I apologize for that, of course, and I apologize for the poor audio quality. His talk is exactly 4 minutes, 56 seconds, so I think we owe him a round of applause for meeting the 5-minute limit.
Okay, thank you, Kevin. Okay, let's move on to the next paper. The next paper is unbounded Hibe with tight security, and the authors are Roman Nacker and Jianxin Pang. And the speaker is Roman. Roman?
Yeah, thanks for the introduction. Okay, I will start with an explanation what unbounded Hibe is. So first, IBE, or identity-based encryption, is an encryption mechanism where you encrypt a message with a master public key that is the same for all recipients, and an identity, that's some meaningful string that identifies the recipient. So for example, an email address. And you have a trusted third party that issues this master public key, and this party can also generate user secret keys. And with user secret keys, you can decrypt messages for one specific identity, but not for other identities. And hierarchical identity-based encryption, or Hibe, is a generalization of this. Their identities are tuples, and you can generate the user secret key for someone else if your identity is a prefix of the other user's identity. So you have this additional key delegation feature. And so the users are implicitly organized in a tree hierarchy as shown on the slide. And in this tree, everybody can generate the user secret key for its children. So you don't have this single party that has to generate all the user secret keys. And usually when you talk about Hibe, you mean bounded Hibe, and that means that the hierarchy depth needs to be fixed in advance. That is usually necessary because either the master public key grows with a hierarchy depth, or because the user secret keys have delegation terms, and these delegation terms typically grow with a number of remaining levels, so the levels below you in the hierarchy. And unbounded Hibe means you don't have a limit on the hierarchy depth, so these two things are not allowed. And this is of course better because it's more flexible and scales better. Okay, the security notion we considered is adaptive CPA security, and the adversary gets, of course, the master public key in the beginning, and he gets access to 2 oracles. The first one is to corrupt a user, so he sends an identity and gets back a use secret key for this identity. And the second oracle is the challenge oracle, where he sends 2 messages and a challenge identity and gets an encryption of one of these messages. And he has to guess which of these messages gets encrypted in this oracle. And of course, he's not allowed to ask a use secret key for a challenge identity or a prefix of any challenge identity, because then he could trivially win. And CPA security, where the adversary also has a decryption oracle, is easy to achieve once you have CPA security for HIBE schemes. Okay, when we prove security of our scheme, we give a reduction to some underlying assumption, and this reduction guarantees us that when we break the scheme with probability epsilon, the underlying assumption can be broken with probability epsilon divided by L, and this L is called the security loss. And you want this to be as small as possible. And with tight security, we mean that the security loss does not depend on the adversary. So in particular, it cannot grow with a number of use secret key queries, a number of challenge queries, or with a hierarchy depth. Okay, non-tight unbounded HIBE, several are now known. The first one in the standard model was by Luke and Waters in 2011. And we also know several tight IBE constructions and also construction for tight bounded HIBE. Yeah, but this is the first construction that achieves tight unbounded HIBE. So starting point of our construction is a tight bounded HIBE that Jessine and me presented at PKC this year. And as you can see, the problem here is that the master public key and the security loss grow with a hierarchy depth. And to get unbounded HIBE, we need to get rid of that. Okay, here's a high-level idea how we get rid of this. So you can see in some sense on a high level, this bounded HIBE is constructed as follows. We take an IBE and use a different instance of this IBE for each levels, and then have some mechanism that glues user secret keys and ciphertext together from each level. And to get unbounded HIBE, we cannot afford to use a different instance for each level of this IBE scheme. So we have to use the same instance on each level. And this makes this gluing mechanism more complicated. And the work by Luke and Waters basically had these structures, but they took the Boni-Boyen IBE scheme, and then they provided a gluing mechanism that could handle using the same instance on each level, and so they got unbounded HIBE. And in our work, we have the same structure, and also this gluing mechanism has a similar structure as the one in Luke and Waters, but a different implementation. And yeah, first of all, this is not black box, so our gluing mechanism is compatible with an IBE version of this HIBE construction I just showed you. And also our gluing mechanism is tight. And since also this IBE is tight, we get a tight unbounded HIBE. Okay, so in the end, we get an unbounded HIBE with the same security assumption as previous works. So here this in prime order pairing groups. We have a tight security reduction, and we have use secret key and ciphertext size that are basically or approximately the same size as constructions before, but we have to pay for this with a larger master public key. And yeah, a nice bonus is that Garg et al. Presented at PKC this year a construction that used tight IBE to construct a master key KDM secure IBE. So this means that the challenge messages can depend on the master secret key. And the same idea can be applied here. So since our construction is tight, we get the first unbounded HIBE that also has this master key KDM security. Okay, thanks for your attention. I'm looking forward to your questions. If there are any.
Yeah, thank you, Roman. I don't see any on the chat. So I would like to ask something. So you had some open questions in your long version of the chat. no, including.
Yeah.
So can you comment on that? So what do you?
Yeah, so as open questions, we proposed either with our technical idea that we use can be used in a more general setting, like general predicate encryption schemes. And I think another interesting open problem is whether you can get rid of this user secret key and ciphertext size or improve on this. So as you can see on this slide, they always grow with the length of your identity, so how deep you are actually in the hierarchy. I think it would be interesting to get rid of that. So for example, constant size, user secret key and ciphertext size.
Do you think would be possible? So is it achieved
I'm not sure
for? Okay.
I'm
so
not sure
is it achieved
possible.
for even non-tight?
No.
Okay.
No, that's not what.
Okay. Thank you.
Okay, I have one more question. How is the actual parameter, concrete parameter size in practice? For example, the master public key size.
So the master public key size, I mean, it grows with a bit length of hashes, so it might be 265 bits. And I think for each hash, you have a couple of groups elements, like I'm not sure, like 10 or so. So it's quite large. So you probably end up with more than 1,000 groups element in your master public key. So yeah.
Yeah. Okay. Thank you. We have one more question. How non-trivial is your tight grooming mechanism?
So on the technical level, so if you look at the details, it's, I would say, highly non-trivial. So I think that's the main contribution of the work.
Yep. Okay, thank you. Yeah. Here is the, okay. The last talk is multi-client oblivious RAM with polylogarithmic communication. And the authors are Sherman Chu, Katarina Feck, Russell Lai, and Giulio Malavolta. And the speaker is Sherman Chu.
Okay, thank you. Let me share my screen. So far so good, right? Okay, and welcome to the talk. I'm Sherman Chow from Chinese U of Hong Kong. So there is a driver with Katharina and Russell from FAU, and Julio who just joined the MPI SNP. And I will try to give a slightly different talk here, but anyway, I need to introduce what is ORAM. So basically, we try to hide the access in terms of whether you are reading or writing, where in the address you are writing, and what is the value. So consider you are like a program, and I am like the CPU. I have my database in the form of n entry array. So you want to read something or write something from me, but I have no idea what you are going on. So the only way you can do that is you try to hide it with a number of physical accesses. For here, that is parameter by L. And for efficiency measure, there is study on the lower bound on L, which should be polylog n, and that is also achieved by a previous construction like path ORAM. So that is in the single client case. So why all the magic happened? The magic happened because you as the client, you maintain a secret state. Okay, so I hope I made myself clear on the basic ORAM. And now, how about the network setting? Consider all you guys are accessing me as a storage server, so how can we do that? Then we can see that as we have multiple clients, we no longer have the luxury to maintain a secret state, and if we consider your fellow client is malicious. So what do I mean by that? So let's consider we have two clients. So we have our usual data owner who delegate the access of database to two clients. So for here, we have our yellow good client pointing two fingers, and we have our malicious green client here, and we have our untrusted server. So in multi-client ORAM, we still consider the database, but we further consider access control. So for example, for this database, the access policy is set up by the data owner. For entry number 2, only client 2 can read and write, but not CAN1. So security property here is still similar but extend to the multi-CAN case. So for obvious list, we want whatever done by the honest client, as long as you don't have the corresponding access right, then the read and write and address and value all remain obvious to any collusion between the server and the fellow client. And of course, if so happen, you also have the read and write, and whatever written here should be readable, and that's by functionality cannot be avoided. So now you can see that because we need to protect against your fellow client, we can no longer use the single ORM technique, because in single ORM there is only one client and it maintains a secret state. And so these two remain indistinguishable. And now we still have integrity requirement, which if you are a malicious client, you are not entitled to write to a particular entry. So this is CAN1. The access control is for CAN2. So the data owners will that means the data owner will enforce this policy through this MCORM technique. Okay, so how do we achieve that? So let's establish the algorithm in a simplified manner. We have our user setup. From a database, we have an encrypted database. We have the key gen algorithm executed by the data owner, and each of the client, after getting the secret key, can access the database by an interactive protocol. So let me skip the formal details due to the interest of time. And this MCORM primitive is actually pretty new, and this first word is appear in SMP, so as a practical construction, but the security guarantee does not hold against malicious client. And later in ACNS 2017, we have a construction secure against malicious client, but the client computation and the communication require all the good n, where n is the number of entry. So now the question is, can we achieve, can we match the lower bound of single client ORM, which without access control, without security against the malicious client? And the answer is, of course, yes. And our main technique here is what we call cross-key evaluation of fully homomorphic encryption ciphertext. So notice that it is not about multi-key. We are still talking about single key, but what do I mean by cross-key? And that is where the technicality kicks in. So that is our usual definition of FHE. And then we have the evaluation algorithm. So with FHE, we try to realize this MCORM property. Read is rather straightforward. We use the standard idea of private information retrieval. The client come up with an encryption key and decryption key pair on spot. He wants to read the address, so he just encrypt the address with respect to this newly generated EK. Send it to server. The server execute this poll circuit, which is parameterized by the database. So that is rather straightforward. Resulting ciphertext after this evaluation will be an encryption of VADDR, where ADDR is encrypted by the client in the first place. And to add access control on top of this, that is also rather straightforward. You just encrypt the database with different keys, different entry with different keys. Then you just give the corresponding decryption key to the corresponding client. So reading is rather straightforward, and writing is what is more interesting. So if we generalize the above idea, that is one thing you can think of. So you want to write something to an address, so you encrypt the address and the value you want to write as usual. But notice that because we are trying to do it with access control, each different entry is now encrypted with respect to different address. So EK1, EK2 for entry 1 and EK2. And so there is one difference. And what this is likewise, we want the server to homomorphically evaluate this function over this encrypted writing or update instruction. So if the address does not match, we want to maintain the original value, because that is not somewhere the client should be writing to. But if the address match, then we update the value. So now you will see the problem is we sort of does not solve this problem at all, because we either need to tell the server what is the address, or if that is trivially but the bit oblivious or leafless, or if we really evaluate this circuit over different entry, then the address will be different. That means the encryption key will be different. That means we are evaluating a ciphertext under a different key, which is not supposed to be guaranteed by a typical FHE correlates definition. So in this regard, we try to upgrade it. So let me try to give you the core idea. Firstly, we call what is the normal evaluation correlates, which if you gave me a whole bunch of ciphertexts, like 2 ciphertexts, encrypted under the same key, then after evaluation, you are guaranteed to get better result if you decrypt it, if you decrypt the resulting evaluated ciphertext. So that is our problem. We don't know what will happen if the ciphertexts are evaluated or decrypted under the wrong key pair. So we try to propose a generic upgrade to take care of this problem. So we need a slightly stronger definition of the decryption requirement, which just want the decryption to be well defined. That means even if you try to decrypt a ciphertext encrypted under different key, it may result in something like a garbage, but it's still within the message space. So that can be garbage. We are not trying to assume away the problem, but we at least require it to be well defined. Then with this requirement, we can sort of bootstrap it to the strong evaluation correlates, which is what we want. So you can evaluate any ciphertext in the ciphertext space. And that is roughly our transformation. So given the well-defined decryption definition and the standard correlates, we have the strong correlates. So with that, that is our core idea. We take care of the above problem. So in the last 10 seconds, I will overview what is our second contribution. So we noticed that that is a highly theoretical construction. So what if we don't use FHE? So our solution here is multi-server setting. So and long story short, we try to propose a distributed upon function-based construction. And meanwhile, we also propose a new construction of DPF, which satisfies parameter that is not satisfied by existing literature. And also there are additional results in the paper. With that, I'm happy to take your questions.
Okay, so thank you very much.
Thank you.
Are there any questions? I see one in the chat from Koan Guyen that says, does the communication cost of your construction depend on the number of clients?
No, it doesn't. I should have made it clear. Thanks for the question. So it's only dependent on the number of entry n.
So I don't know if there are any more questions because we should wrap up soon. So. Okay, so I think we should finish the session because it's already 7:21. Well,
thank you very much.
Sorry, in my time zone, sorry. So thank all the speakers for these nice talks. And I don't know if Yun Tang wants to add something. Okay, so